Okay, for this one, they're asking us to find the derivative of the inverse when x is equal to -3. Remember, the -3 is an x value for the inverse, but it's actually a y value for the original function. Okay, you can use your calculator to solve this if you want, but what I sometimes do is I'll try to plug in an easy number like 0, see if it works. E to the 0 is 1, and you can see that 0 does work. We could also solve this with a graphing calculator. Okay, again, the equation I'm trying to solve is the equation in red. Put a box around it. Again, we have to push F2 to get solved. I'm going to solve for x. I'm going to push comma x. I'm going to go back inside and then put the equation. Push enter. And it's telling us x is equal to 0 is the solution. Again, you can plug that in if you want to make sure. You plug in x equals 0, you will get -3 equals -3. Okay, remember the rule for the derivative of the inverse? It's going to be 1 over f prime of x. So we have 1 over the derivative of f. So here's f right here. We need to do the derivative of it. The derivative of x to the third is 3x squared. The derivative of e to the x is just e to the x. And 7x minus 4 is just a line. So the slope of that is just going to be 7. Now this is 1 over f prime of x. We just figured out that our special x that we're going to plug in is going to be a 0. So we need 1 over f prime of 0. And that will give us 1 over 3 times 0 squared plus e to the 0 plus 7. Of course, e to the 0 is 1. So our final answer is going to be 1 over 8. Again, that's just a review example. Okay, for this example, they're giving us the graph of f prime, and we have to find out a bunch of stuff about f. So the first thing is, what are the critical numbers? The critical number is going to be where your derivative is either 0 or undefined. We don't have any spots where our derivative is undefined, but we have 2 spots where our derivative is equal to 0. So when x is equal to 4 and when x is equal to 10, we have 2 critical numbers. So that's going to be the answer for the first part. Okay, for the second part, where does f have either a relative max or a relative min? Okay, because we're looking for a relative max or relative min, we can go ahead and ignore the endpoints. You can see that the original function is going to be decreasing, and then decreasing, and then increasing. So decreasing, decreasing, then increasing. So you probably have possibly an absolute max at the beginning, and also at the end you might have an absolute max. It just depends on which endpoint is higher. We can go ahead and ignore that because we're just looking for relative max or relative min. Now, in order to get a relative max or relative min, your derivative does have to cross the x-axis. In this case, we're decreasing, then we're decreasing, and then we're increasing. So that spot, which is our critical number of x equals 10, is where you're going to have a relative minimum value. Okay, the next thing we need to find out is the inflection points of f. Remember, if you're looking for inflection points, you're looking for the second derivative to change signs. In order to get the second derivative from the first derivative graph, you're going to have to do the derivative of f prime. The derivative of f prime will equal f double prime. Another word for derivative is slope, so we need the slope of f prime, and that's going to be f double prime. So the slope of f prime is going to be positive, then negative, then positive for the rest of the way. In order to have an inflection point, we need our second derivative to change signs. That happens at x equals 4 and x equals 8. But we also need to have a tangent slope at that spot. In this case, we do. The tangent slope when x is 4 is going to be 0. And the tangent slope when x is 8 is going to be -4. So both of those are going to be inflection points. Again, these are just the x values of the inflection point. We can't actually find the y value without the original function. Okay, the next part wants to know where f is concave down. Well, f will be concave down where our second derivative is negative. Remember, we filled out the second derivative by putting these little pluses and minuses. So our second derivative is going to be negative in between x equals 4 and x equals 8. So this is where our function f is going to be concave down. Okay, now we need the equation of the tangent line when x is 2 and y is 5. So we have our point, we just need the slope. So what is the slope when x is 2? Well, this graph tells us the slope for any x value. So you can see when x is 2, the y value is -2. So our y value is actually our slope. So we're going to say our slope is -2, and we'll use our point of 2, 5. Equation of our line is going to be, and you can stop there, but a lot of people like to solve it for y, so let's do that. Okay, there we go. That's the equation of the tangent line on the function f at the point x equals 2, y equals 5. Okay, the last thing we're going to do here is we're going to try to draw the graph of f. It's just going to be a sketch. Remember that 2, 5 was one of the points. Okay, let's go ahead and plot our point, 2, 5. And that'll be the only point that has to be 100% correct. Now I want you to notice that we are decreasing until x equals 10. So I'm just going to use straight lines for that. And then we're increasing after x equals 10. So we expect a relative min at x equals 10. We don't know the y value. Now we can add the curvature. We can see that f is going to be concave up, and then concave down, and then concave up. We can also see the slope should be 0 when x is 4 and when x is 10. Okay, your sketch should look something like this. I want you to notice that our first derivative is negative until you get to 10. So our function should be decreasing all the way till 10. I also want to point out that our first derivative is positive after 10. So our original function should be increasing after 10. Also, our second derivative is positive between 0 and 4. So that means our original function should be concave up between 0 and 4. Then our second derivative is negative until you get to x equals 8. So our original function should be concave down until you get to x equals 8. After x equals 8, our second derivative is always positive. So we would expect our function to be concave up after x equals 8. You see that we are concave up after x equals 8. Remember, our derivative changes from negative, which would be decreasing for our original function, to positive, which is increasing for our original function. So at x equals 10, we change from decreasing to increasing. So we would expect to have a relative minimum at that spot where it changes. So here's our relative minimum. So notice x equals 10 is where you see a relative minimum value. Remember, this is just a sketch. The only point that has to be 100% correct is the point 2, 5, and that's because that was given to us. Okay, this is a similar problem as what we just did. Only difference is we don't have the graph of f prime. We have a table of values for f prime. They're also giving us a table of values for f double prime. First thing we want to find is what are the critical values for f. Well, a critical number or a critical point is where your first derivative is either 0 or undefined. So we can see where our first derivative is either 0 or undefined. So those will be our critical numbers. Remember, if you're going to have a relative max or relative min, it would have to happen at one of those points. So for the first part, our critical numbers are going to be A, C, E, and F. Okay, now that we've found the critical points for f, I actually want to go down to the bottom and draw the graph of f. The hard part about this is that all we have is the first derivative and second derivative at some of these x values, just some spots. So we don't actually know what's happening in the middle. So we're going to just have to do our best to sketch the graph when we know exactly what's happening at each x value. So we'll start with x equals a. We know the first derivative is 0 and we're concave up. So that's going to look something like this. First derivative is 0, so we have a tangent slope of 0, and we're concave up. When x is b, we should be increasing, but we're not concave up or concave down, so we're just going to be increasing at a constant rate. That's going to look something like this, so it looks a little bit linear. When we get to x equals c, we're going to have a horizontal tangent slope, and we're also going to be concave down. That's going to look something like this. When we get to x equals d, we're going to be decreasing. Second derivative is 0, means you're not concave up and you're not concave down. So usually we just put a line for that. At point E, we're going to have a horizontal tangent slope. And again, we're not concave up or concave down, so it's just going to be kind of like a line. Now at point F, our first derivative is undefined, and so is our second derivative. And there's a lot of ways to do that. You could have a sharp corner. You could have a hole in your graph. You could have an asymptote. And we don't have any additional information to tell us which one to choose, so I'm just going to put a sharp corner. Now at point G, we're going to be increasing and concave down. Now we want to do our best to connect all of these. Again, we don't know exactly what's happening in between those points, so I'm just connecting them. It could be doing a lot of different things. So this is what we call a possible sketch of f. Now, after doing a possible sketch, you'll notice that it looks like we do have a relative max at x equals c. It also looks like there's a relative min at x equals a. Now, at point f, if your function is continuous, then you would have a relative min there. But remember, it could possibly have been an asymptote or even a hole in your graph. So we're not really 100% sure of what's happening at point f. If this was a real question on the AP test, they would have to be more clear. They would have to say that the function was continuous everywhere, or they'd have to give you more details. Are there any inflection points? Well, we're looking for our second derivative to change from either positive to negative or from negative to positive. Because our second derivative is 0 at point B, we don't really change from positive to negative at point B. So I don't see any inflection points. Again, there could be inflection points, but we don't have a full picture of what the graph actually looks like. All we have is the first derivative and second derivative at certain points. So we're missing a lot of the real graph.